So in the last section we discussed dimensional analysis, and in this section we'll discuss scaling analysis. Scaling and dimensional analysis, the two terms can be used sometimes a bit interchangeably. They are related, but here I'm referring to dimensional analysis when you're really reasoning on the dimension and on the units. So that's what we discussed last time. And I refer to scaling analysis as a more intuition-driven, based on physical principles way of finding the non-dimensional groups which are relevant. So the goal for scaling analysis is still to determine which one are the non-dimensional groups which are relevant to the problem, and that will allow you then to find what are the dominant physical parameters in the problem. Alright, so scaling analysis is the way I will use it here and describe it here is a little bit less systematic than dimensional analysis, and oftentimes I think is easier or is more useful. At least this approach is how I usually do things. And the idea is to simply look at a physical problem and to determine the interdependence between the different physical parameters based on a physical intuition which is grounded into pre-knowledge of the laws of physics. So determining the interdependence between those physical parameters by reasoning based on physical intuition, and that physical intuition is often grounded in knowledge of the relevant laws of physics. Okay, so this is may sound a little bit abstract, so let's take the same example as the one we took for dimensional analysis. So we have our pendulum, and again we are still interested in the frequency of the oscillations. So now we still have to think about what are the relevant physical parameters, but this time we're already thinking about the relevant laws of physics behind this. It's not just reasoning with dimensions. And you know what is the law of physics governing the oscillation of this pendulum? It's Newton's second law. Right? So you already have this idea that the mass is going to be important. The frequency is of course what we want to know. Sorry, so it's going to be one of our parameters. It's moving because of gravity, so the gravitational force is going to be important. So gravity should be one of the parameters, and then the Newton's second law will have to do with acceleration, with changes of velocity. So there has to be a length scale, and the length scale which is in the problem here, the only one that we have, is really the length of this level arm here. And then there's not one way of doing scaling analysis. So scaling analysis is not a rigorous exercise. It's a little bit more like kitchen. There is like cooking. There is a little bit of a recipe, but everybody does it a little bit differently, right? So the way I approach this is just to think about the equation which I would write. The physical principle governing the oscillation of the pendulum is Newton's second law. So in Newton's second law, we would have mass. The mass of the pendulum times the acceleration of the pendulum, and that would be equal to the gravitational force somehow, which is what drives the system. Right? So we would have a law that looks like this. Now we need a scaling for the acceleration. So how does the acceleration scale? So the first thing we need to do is to come up with a scaling for the acceleration. So the acceleration is represents the changes, the rate of change with time of the velocity, and the velocity is the rate of change with time of the position. So what is the scaling for position? So the position of the pendulum, so the pendulum is going to oscillate here, between here and there. And so if we have to think about what will be the length scale of this motion, the length scale of this motion is going to be on the order of L, on the order of this lever arm here, the length of the pendulum. Alright, so if the position scales with L, then what is the scaling for the velocity? Well, the position is going to change on an order of magnitude of L over a time scale, which is the period, which is 1 over the frequency. So a scaling for the velocity is going to be L times the frequency. Now what is the scaling for the acceleration? Now then again, the acceleration represents the rate of change with time of the velocity. And the velocity goes from about 0 at this position of the pendulum, to a maximum velocity here. So the time scale for the acceleration, for the change of velocity, is also f. So the scaling for the acceleration is simply going to be the scaling for the velocity divided by the time scale, which is the period, roughly the period of the oscillation, and therefore the scaling for the acceleration is L times f, which is the scaling for the velocity, times f. And so from the scaling analysis, we can deduce that m. So this was our physical principle that we started with, and what we find now is that m times the scaling for the acceleration here, which is L f squared. We just deduced it here. This should scale with m times g. The m's cancel, and you find a theoretical scaling for your frequency, which is the square root of g divided by L. Now again, scaling analysis doesn't give you the right answer. We have this 1 over 2 pi factor missing, but the dependence of the frequency on G and L is present in the scaling. So this is how you do a scaling analysis.